So up to this point, sorry, the screen keeps changing spots. Up to this point, we have made an assumption that the permeability of our core materials is a constant value. And that is unfortunately not the case for the overwhelming majority of ferromagnetic materials. So we are going to review ferromagnetic materials in more detail and start looking at how we can incorporate effectively data sheets and things like that into our analysis of magnetic circuits. All right, so magnetic materials that include certain forms of iron and its alloys in combination with cobalt, nickel, aluminum, and tungsten are called ferromagnetic materials. We've already talked about this. They are relatively easy to magnetize since they have extremely high relative permeabilities where mu r is much, much greater than 1. We also talked about this on our first day of class. What we didn't talk about is why they behave in that particular way. So ferromagnetic materials contain what are called Weiss domains, which are small regions in which the magnetic field of the constituent atoms are aligned. So I'm going to draw a crappy picture here, trying to explain what I mean. And I am going to be lazy and replicate this picture 3 times over. So just giving you fair warning. Make a copy of this. And paste. Copy right here. And then paste another copy over here to the right. All right, so these boundaries that I've attempted to draw here are something similar to what the Weiss domains in a crystal might look like. So prior to us magnetizing our crystal, meaning that we wrap a wire around the core and pass a current through there so that we're forcing some amount of flux through it, these domains are going to be randomly oriented, okay? So our magnetic field lines for this particular domain in the top left might be in this direction. In this domain, they might be down. In this domain, they might be up. We might have some down and to the left, diagonally down and to the right, directly to the left, up and to the right, down and to the left, etc. They're just supposed to be randomly aligned so that we don't really see any net magnetic field in any particular direction, okay? Now, if our material, our ferromagnetic material, is subjected to an external field, the atoms in the material will tend to align themselves in the same direction as the external field, which is going to increase the amount of flux that's passing through the material, okay? So let me denote this is before magnetization. And then this picture here is going to be effectively during the process of magnetization. And so we're going to see that generally speaking, if our external field was, let's say, directed from left to right, everything that was already left to right is going to be pretty much the same, but everything that wasn't oriented left to right is going to start turning left to right. So now we have a little bit of field directed in one particular direction, okay? If we increase the amount of current passing through our coil and causing more flux to flow through our crystal, what we're going to see is that our magnetic field lines in our Weiss domains align more and more and more with the direction of our applied magnetic field until we hit a point where everything is perfectly aligned. And let's say that we have all of our Weiss domain field lines oriented directly from left to right, right? So this would be like under a strong external magnetic field. Now, what would happen if we were to pass even more current through our coil? Anybody have any thoughts on that? So we know that our magnetic field strength, H, is proportional to the amount of current that we apply, right? So if I is larger, the value of H is larger. So we should expect to see that our magnetic field lines line up because we're in the presence of a strong external magnetic field. But at some point, we can only get parallel, right? We can't get any more parallel than parallel. So if we apply more current beyond us hitting this point, literally nothing happens, okay? We call this saturation because an increase in our input signal, which is our current, doesn't cause any change in our output, which is how our field lines line up, okay? So this is typically quantified in what's called a magnetization or BH curve for the material. So we're going to see something like this. Okay. So on the y-axis, we are going to have our magnetic flux density measured in Tesla. And on the x-axis, we are going to have our magnetic field strength, H, measured in amp turns, can't spell, per meter. Okay. And so if we're dealing with a DC current, we should see something like this, right? So we're going to have a linear increase up to some point. Then it's going to start to turn. And then after a while, it's going to stay flat. So there are three specific regions here, right? So here we have what's called the linear region. So this is where our field lines are starting to line up. Then we have the knee of the curve, where we're about to hit saturation. And then finally, we hit the saturation region, where an increase in our H field no longer causes an increase in our B field. If an AC current is used to create a time-varying external field, we're going to see something very interesting happen, okay? This is what's called a hysteresis curve. So this is going to be just a BH curve like we have above, except that we're going to allow the H field to come back down and turn negative, like our current change direction. Okay. So once again, this is magnetic flux density measured in Tesla. This is our magnetic field strength measured in amp turns per meter. And as we start our cycle, we're going to have something like this. It's going to look almost identical to our previous thing. Linear increase, and then it's going to kind of flatten out like so. And this is our direction, okay? But what's going to happen? Yes, Bailey. Saturation. Okay. So I'm going to call this line from O to A, okay? And I'm going to describe what's going on down here. So for the segment O to A, the material undergoes saturation, excuse me, magnetization until saturation is reached. Okay. So we've hit a point where a subsequent increase in our H field doesn't cause an increase in our B field. Now, what's going to happen when we back off our current or we reduce our H field? So instead of going straight back down to where it was, instead we're going to see something like this. So it's going to come down and then it's going to stay at some value here. So this point is B, like so, and we can see that we have some residual magnetization. This is literally how permanent magnets, like man-made permanent magnets, are created. We put a ferromagnetic material in the presence of an external electric field until we saturate it, and then we slowly back down off that field until our current is zero so that we can safely remove the material, and the material has some leftover magnetization, which is why we can stick it to our refrigerator or whatever the hell else we want to do with our magnet, right? So we have some residual magnetization. It takes us applying an external field in the opposite direction in order for us to actually demagnetize our material. So this will be point C. So let me write some things down here. So for the segment A to B, the current has switched direction. And the material is being demagnetized. However, when H returns to zero, B still has some positive value, which we're going to call B res, for B residual, which is characteristic of the residual flux density in the material. Then for segment, scroll down here, and I'll go back up to the image in a second. For segment B to C, we apply what's called a coercive MMF to bring our B field back down to 0. So it requires extra energy effectively for us to completely and utterly demagnetize our material. If we continue applying a more negative current or a more negative H field, we will eventually wind up saturating in the opposite direction. So this would be point D. So at this point, the field lines have completely and utterly switched direction. So if they were from left to right earlier, now they're from right to left. And then if we increase our current or increase our H field, the curve just repeats itself in the other direction. Like so. And it's going to cycle like this over and over and over again. So, a couple of things that we can notice from this. One may seem a little odd, but effectively, magnets have a memory. They remember whether or not they have been previously magnetized, or ferromagnetic materials have a memory. They remember whether or not they have been previously magnetized. That leftover magnetization that we see right here and right here is effectively this memory. This is the reason that magnetic materials or ferromagnetic materials were used for computer storage up until the last 10 years or so, right? All of our old platter style hard drives, all of our old floppy disks and all that kind of stuff is literally a magnetic material that we are magnetizing certain bits to make them look like a digital 1 or demagnetizing other bits to make it look like a digital 0. And because we have this residual magnetization that stays around, they maintain their memory state until we put them in the presence of an external magnetic field to change the state of those bits, right? So this hysteresis literally describes how data was stored for the better part of 60 years. Okay. Another thing that's interesting about this is effectively takes energy to do this, right? So we are going to now talk about the losses that we will observe in repeatedly magnetizing and demagnetizing a magnetic core material. And we're going to call these magnetic core losses. Okay, so we're starting to look at real things now as opposed to ideal. So when a magnetic material is subjected to a time varying flux, magnetic flux specifically, the material experiences energy losses which we typically call core losses. These losses can be attributed to two different phenomenons, phenomena, whatever the correct plural of that is. So one of them is called hysteresis loss. Sure. Yes. Hysteresis, hysteresis. That's what that fancy curve earlier was called. That's correct. Magnetic core losses. Yes. Okay. So hysteresis losses is one of the two major phenomenons that we associate with magnetic core losses. When a magnetic material is subjected to an external magnetic field, the magnetic domains tend to align, with the external field, which is what we've already described. Hysteresis losses are just the energy required to change the direction of the domain's magnetic field. When subjected to an AC coil current. And so I'm going to hit you guys with an equation now. P subscript H, so power subscript hysteresis, is equal to capital V. I'm going to define all of these things. Lowercase f, K subscript H, B subscript max raised to the nth power measured in watts, where V is the volume of the core material measured in cubic meters. So effectively, the more material we are magnetizing, the more losses we experience. F is the excitation frequency. Measured in hertz. So effectively, if the more quickly we try to change the direction of the magnetic domains, the more losses we incur. K sub h is a proportionality constant of the core material. So that different materials will experience different hysteresis losses. B max is the maximum magnetic flux density seen by the core, measured in Tesla. And lastly, N is what's called the Steinmetz exponent. Steinmetz. Apparently the guy that came up with this equation wanted to put his name on it somewhere. So he got to put his name on the coefficient. So the Steinmetz exponent, which is typically somewhere between 1.5 and 2.5, depending on the material. So this is how we mathematically calculate the hysteresis losses. I'm more concerned that you guys understand what are going to cause larger losses, right? So the big things here are the more material that we are trying to magnetize, the larger the losses that we are going to see. And the more quickly we try to magnetize and demagnetize the material, the more losses that we are going to see. Yes. And so is the Steinmetz coefficient. Or exponent, or whatever the hell I have written down here. All right. So this is one of the phenomenon that causes, or that we attribute to magnetic core losses. Now let's talk about the other one, and you may have heard about the other one before. Have any of you guys ever heard of what's called eddy current losses? No. Okay. That's all right. So because iron is a conductor, time varying magnetic flux induce opposing voltages and currents that circulate within the core. So I'm going to draw a picture here, and I'm going to ask you guys a question. So I'm attempting to draw just kind of like a rectangular rod of material. So this blue thing is our core. And then as per usual, I'm going to wrap a wire around it. Okay. So let's say that I have a wire wrapped around it in this direction, and the arrow is indicating the direction that my current is flowing. I'm just going to wrap the wire around this thing a whole bunch of times. Like so. And here's the return path for my wire for all intents and purposes. So what should the direction of our magnetic field be that's passing through this core material based on the direction of our wire, right? Should be directed out of the rod. Right? So something like this. So this is the direction of our magnetic flux that's generated by our coil, and it's told to us by the right-hand rule, right? If our fingers of our right hand wrap around in the direction of the winding, our thumb points in the direction of the magnetic field, and flux is nothing more than just the amount of magnetic field per unit area kind of thing. So it's going to be in the same direction as well. Okay. Have you guys heard of a thing called Faraday's law of induction before? Okay. And have you heard of a thing called Lenz's law? Okay. So what does Faraday's law of induction tell us? Anytime that we have a time-varying magnetic field, we induce voltages and currents in a system, right? Lenz's law tells us that these induced voltages and currents occur such that they're trying to keep the flux constant, right? So if we are passing an AC current through this coil here, then the length of this flux vector is effectively constantly changing, and it'll be long, and then get shorter, and then it'll turn around once the current changes direction and all of that kind of stuff. So it'll like sinusoidally vary. Well, our induced flux, our induced current in our wire will also cause a magnetic flux, and its job, according to Lenz's law, is to keep the net flux at a constant value. So effectively, nature abhors a change. So the direction for our induced flux is going to be something like this. So phi b induced. They are in opposite directions to each other because they're trying to keep the flux at some constant value. So these all right, so actually, sorry, let me go back a bit. So we looked at the flux there. Let's look specifically at the current that's going to generate that flux. So this is going to be my induced current, okay? So if I have a flux that's oriented in the opposite direction of our coil flux, then that means my induced current has to be flowing in the opposite direction of my coil current, right? So something like this. So this would be I induced with this direction circulating around like this so that we get a magnetic flux opposite to our coil flux. Now, I'm going to ask you guys, hopefully a pretty simple question. What happens when I pass current through a conductor? It heats up, right? Wires get hot when we pass current through it. So effectively, these eddy currents are going to cause my core material to heat up, which is going to cause my magnetization to go down, because magnetization is a function of temperature. So I'm going to lose magnetization, so I have losses that are attributed to these eddy currents, right? So the more I heat my crystal up, the more losses I have because my overall field has gone down. Thinking about talking to you guys about how rice cookers work, but I'm going to not bore you with that. If you want to learn about it, it's literally based on this, and we can talk about it later. So what could we do to minimize eddy current losses in our system? Well, okay. So we can lower the temperature, so we could try to cool things down. Absolutely, that's one way to do it. But let's say that we have an electrical transformer or something like that, which is where we're getting towards, and it's out in open air in a housing or something like that. We don't really have a whole hell of a lot of control over the ambient temperature of our device, right? Unless we specifically build in cooling, and we do to some extent. So let's think of something different, right? So the more material that my current passes through, the hotter it's going to get. So I need to try to figure out how to limit the amount of material that my eddy currents can pass through. So what we wind up doing is we actually like slice and laminate our cores. So we take our magnetic core material. Let me draw a picture over here. So basically the exact same structure. I wish I had brought a transformer or something over from Nethkin to where you could see this, but you could give it a Google or something like that. And we literally just slice it up. Like so. And we separate these regions of core material by very, very thin. And I'm talking like tenths or hundredths of a millimeter thick insulator materials, so that our eddy currents can only flow around these smaller paths, and therefore they heat the material up less. So the thinner the laminations that we can get and all of that kind of good stuff, the less eddy currents that we're going to see. So mathematically, scroll down here, our eddy current losses are given by the following equation. P sub E. By the way, this is just a quick aside, but eddy currents aren't named after some dude named Eddie. They're called eddy currents because they circulate around like eddy currents in a river or something like that. So we're going to have K sub E times V times F times T subscript L times B max quantity squared. And because it's a power, it's measured in watts. Once again, capital V is our volume of material. So the more material we have, the more losses that we incur. K sub E is a proportionality constant for the material. F is once again our excitation frequency. Measured in hertz. And then T sub L is our lamination thickness. So the thicker our laminations are, the more losses that we incur. So we want to slice it as thinly as possible. Our lamination thickness is measured in meters. And then B max is once again the maximum magnetic flux density seen by the core. So we have a lot of control over the amount of eddy current losses that something that we design can experience, because we get to decide how thinly we slice our core material, how thickly we put our insulating material, and all of that kind of good stuff in. So I want us to work an example problem for a magnetic core. And I want us to find the required coil MMF needed to produce a particular maximum flux. Because we're going to be dealing with a real material, we're going to have to look at the magnetization curves that I provided to you guys. And I'm sorry that on this front page, it's all blurry. I got this from a textbook. On the back page, there's some stuff that you're going to use for, I think, the in-class assignment. And then in your homework assignment, I actually just made up materials so that I could have nice, pretty graphs for you guys to use. So anyway, so let's look at this example. So let's say that we have a core having the following shape. It's going to be a horseshoe kind of thing. Like so. I'm going to put my coil over here on the left-hand side. Let's say that I of t is flowing in this direction. Let's say that our core is made of M-1929 gauge sheets of steel. And our stacking factor is 0.9. So let me explain what I mean here by a stacking factor, right? So I talked earlier about how we laminated our sheets together and they're separated by insulators. So the stacking factor is effectively telling us how much of our core is actually core material, and then whatever's left over is the insulation material, right? So 90% of this thing is actually M1929 gauge sheets of metal, and then the remainder of the physical structure is that insulating material. That's all the stacking factor means. Okay. So let's say that this dimension is W, this dimension is W, this dimension is W, this dimension is W. We have a gap length LG. We have a distance here, L2. And a distance here, L1. So I believe the geometry of the structure is identified. So let's say that L1 is 10 centimeters. L2 is 15 centimeters. LG is 2 millimeters. The width is 1 centimeter. And our thickness is also 1 centimeter. And we are trying to figure out the required coil MMF needed to produce a maximum flux of 125 microwebers. So I want to point out a couple of things here. I did not give you a core permeability or anything like that because we are going to use this table to figure some things out, okay? So what information do we have about this thing? We have its geometrical quantities, and we also have some amount of maximum flux that we're trying to achieve, okay? So the first thing that we're going to need to calculate here is going to be the area of the core that our flux sees as it travels through it, okay? So I'm going to call this AC, so core actual. And this is going to simply be the nominal core area times our stacking factor. So what is the nominal cross-sectional area that our flux sees as it travels around this magnetic circuit? The width times the thickness, absolutely correct. So our actual core area is just going to be the width times the thickness times our stacking factor. So that's going to be, 1 centimeter times 1 centimeter times our stacking factor of 0.9 gives us 0.9 centimeters squared. Everybody okay with that? So we know that 90% of our material is the actual sheets. So 90% of our cross-sectional area is what's going to be used. Okay. So using this information, what is the flux density in the core going to be? That's just going to be our flux divided by our actual core area, right? So 125 microwebers divided by 0.9 centimeters squared. And this comes out to be 1.389 Tesla. And I'm going to call it 1.4 Tesla because that's something I can find on my sheet more easily. So now I'm going to pull up that sheet. It's the ELET 360. Magnetic materials handout. So I have this terrible blurry sheet. Like I said, I apologize for the shitty resolution. Tried to make it nicer for other things. Okay. So we are dealing with M1929 gauge sheet. So we're looking at this top curve. So we know that our flux density was about 1.4. So I'm literally just going to draw a line over here until I hit this thing at 1.4. And then I'm going to go down, 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 down. till I find the H value that corresponds with that, which is, yeah, so let's call it 1100. Roughly, right? The best we can do is estimate things here, okay? So using our magnetization curve, we can say that H in our core is approximately 1100 amp turns per meter. And from this, at this particular point along our curve, our core has a permeability of the magnetic flux density divided by the magnetic field intensity. So that would be 1.389 Tesla, 1.4 Tesla, whatever you want to call it, divided by 1100 amp turns per meter. And this comes out to be 1.263 times 10 to the minus 5 henries per centimeter. And now effectively, this problem is just like any other problem that we've worked to this point. It's just a simple magnetic circuit. We know what our core permeability is. We know what our cross-sectional area is. We know what all our dimension is and all that kind of good stuff. And so now we're just trying to solve for MMF. Okay. So that's how we incorporate real materials and how they behave into the magnetic circuits that we've been dealing with. Right. So our ultimate goal was to find magnetomotive force, MMF, right? Using our Ohm's law relationship, MMF is equal to nothing more than flux times reluctance. We have the flux, and now we have enough information to calculate reluctance. So how am I going to break this core up? I have a left leg, I have a top leg, I have a bottom leg, I have something on the right, and then I also have that gap, so I'm just going to calculate those four reluctances, right? So let's start with the reluctance of the left leg. So what distance does my flux travel when it goes along the left leg? L1 minus W. Yeah, so we're doing the same boring stuff that we've been doing now, okay? So L1 minus W divided by mu C times AC actual, right? And plugging in our numbers for this, we're going to wind up getting 7.920 times 10 to the 5 amp turns per watt. The top and the bottom are going to have the same reluctance. So what's the length that the flux travels along the top or bottom leg of this thing? L2 minus W, right? Divided by that same mu C times AC actual, plugging in numbers, we would wind up getting 1.232 times 10 to the 6 amp turns per Weber. What length does our flux travel through the core on the right-hand side? L1 minus W minus LG. Absolutely correct. Great job, Bailey. So L1 minus W minus L sub G all over mu C times AC actual. And that came out to be 7.744 times 10 to the 5 amp turns per Weber. And then lastly, we have the reluctance of our air gap. So that's just going to be the length is the length of the gap. That G looks like a Q. What's the permeability? Mu naught. Good job. Trying to trip you guys up and you're too damn good. What's the area that the flux sees as it passes through the air gap? Do we need to incorporate the stacking factor? No, hell no. The stacking factor is only for the core, right? So this is just the air outside. So it's just looking at the absolute dimension. We don't need to take into account that. Great job, Caitlin. So the width plus LG times the thickness plus LG. So that's mu naught times A. All right, so that comes out to be 1.105 times 10 to the 7 amp turns per Weber. And then our equivalent reluctance is just R left plus, I'm going to call it twice R top plus R right plus R gap. And let me get a calculator out so I didn't write this number down. So let's see, 7.920 times 10 to the 5 plus twice 1.232 times 10 to the 6 plus 7.744 times 10 to the 5 plus 1.105 times 10 to the 7. 1.526. Come on, Ron, I can't be boring you too. 1.526 times 10 to the 7 amp turns per Weber. And then finally, our MMF would then be phi B times REQ, which comes out to be 1,855.353 amp turns, which tells us effectively that either we need to be comfortable passing a whole hell of a lot of current through our coil, or our coil needs to have a whole lot of windings in order to sustain this particular amount of flux in M1929 gauge sheet core material. All right, so that's enough ranting out of me for today. You have an in-class assignment, so work on that. If you have any questions, I'd be happy to answer them. Sure.
I'm 2 on it. I don't know if I'm doing it wrong or what, but I can't seem to get the same exact REQ that you're getting.
All right, so let me see what you got here.
I don't know if I'm just solving for equivalent resistance wrong, but
Let me pull up the assignment sheet because I don't remember literally anything. So this would be winter 2024. Homework 1. Apparently I did not save it as a PDF, so let me open it up in Word. So are you close to my answer?
Yours is like 8.5.
Okay, so that's pretty appreciably. Oh wait, 8.5?
I'm getting 9.2.
Okay. Open the damn. No, I don't know. Right over there, Lindy. Sorry for that. All right, so you're saying,
Number 2.
oh, for number 2.
Yeah.
All right. So got all this crap defined. So the right leg, the middle leg, and the left leg, the middle leg, and the right leg should all be the same thing. So that is L1. I didn't
label it as.
Yeah, no, that's fine. I'm sorry I didn't label it. That's definitely confusing. So L1 minus W, because it's half a W on both sides. All right, I agree with that. And then the cross-sectional area would be the width times the thickness, okay? And then 15,000, so 4 pi times 10 to the minus 9. So that all seems legit there. Let me just throw this on my calculator just for shits and giggles. So 50 minus 10, I'm just going to call that 40 over 10 times 8 is 80 times 15,000 times 4 pi times 10 to the minus 9. 26, 52, blah, blah, blah. So a little bit of rounding there. I'm going to store this in my calculator.
That's what I did too. I just wrote it like that.
Yep.
And
all right. Then we have the top left, the bottom left, the top right, and the bottom right are all going to be the same. I agree with that. The length is going to be half of L2 minus half of W. Okay. So 0.5 times 80 minus 10. And then width times thickness times VC. So let's see. So 80 times 15,000 times 4 pi times 10 to the minus 9. 2321 times 10 to the 3. Let's store that as Y.
And then when you're solving for the equivalent resistance, you do it from looking at it from there, right?
Right. So we would see these 3 things in series.
And
those 3 things are in series, and it's in parallel with that one. Okay.
But then once you find that, you should be able to add all those.
Yeah. So let's see. So this leftmost leg is going to be 2y plus x. That's going to be in parallel with x. So answer times x divided by answer plus x. And then I'm going to add to that x plus 2y.
Okay. Yeah, I did that.
Wait. No, sorry. I think I made a mistake there. This was y, so it should be 2y plus x up here. $72.94. Right, so make notes so I don't screw this up again. So this guy was x, and this guy was y. So 2y plus x, okay, times x divided by answer plus x. So that's that stuff in parallel, and then plus 2y plus x. $92.39 and change.
That's what I'm getting, but the answer on it is 8 point.
Looks like it's my mistake.
Okay.
I don't see anything. I'll go back through, fix it. You know me well enough to know I screw shit up.
That's what I wanted to ask.
Yep. Yeah, I'll go back through and I'll double check that. Can you shoot me a quick email to remind me to do that? Yeah, thank you. I want it in engineering format and my graders will be dicks about it. Yeah. I don't care about the discussion section. Just to be clear, that's a waste of everyone's time, but I do want it in engineering format. Do not do the discussion. It's a waste of time. Yeah, and you don't need to handwrite out the problem statement and all that kind of jazz. I think I provided you with things in doc format so that you can literally just copy paste that crap.